Hi all, today we'll look at cosine distance and similarity. Initially conceived as a video about metric classes, I decided to split it into a few shorter clips for convenience. So, cosine distance it is. In daily life, people usually use regular old Euclidean distance, or the square root of the sum of squares. But sometimes it is beneficial to use angles as a choice of metric. And the first question that immediately pops into our minds is why cosine? Well, since we only know the coordinates of some points in space, maybe these are embeddings, maybe not, we need to find a way to convert them into something we can measure angles with. In this case, cosine works, and here's how. Right now we have coordinates for the points, but we can also treat them as vectors. Since these vectors have common origin, we can measure angle between them. Now we just need to compute that angle, and we'll do that through cosine, since cosine of such angle is a dot product between vectors normalized, meaning each vector is scaled to have a length equal to 1. So we need to do just a couple operations that are simplish for modern computers. We need to normalize our vectors and compute dot product between results. This cosine is also called cosine similarity, because it measures how similar these vectors are. By similar, we mean that if they point toward the same direction, cosine similarity will be equal to 1. And if they point in opposite directions, cosine similarity will be equal to -1. Okay, but now we need to do something about distance, because distances usually are non-negative, right? So we can just take 1 and subtract the similarity. Then, if our vectors are aligned or pointing toward the same direction, the similarity is 1 and the distance is 0. And if they point in opposite directions, then the similarity is -1 and the distance is 2, which is the largest possible. And it makes sense. If the angle is small, then the distance is small too. And if the angle is large, then the distance will also be large. Why is it useful? Sometimes it is much easier to work with compared to Euclidean distance, because the cosine distance between any two points cannot exceed 2. We can also modify our neural network to provide already normalized embeddings. Then all the outputs will end up on a sphere with radius 1 around the origin, aka unit hypersphere. It is nice to work with data when we know that values are bounded. Well, that's all for today about cosine distance. Next time we'll talk about contrastive losses, so don't forget to subscribe. Thank you.